All right, so I'm just going to start by going over vectors a little bit. And so to talk about what a vector, another notion, which is the notion of a scalar. Okay. So a scalar is a quantity that has only a sense of magnitude, but no sense of direction. So let's say that scalars have only a magnitude. And then in contrast, a vector is a quantity that has both a magnitude as well as a direction. Okay. And maybe giving some examples of quantities which are vectors and quantities which are scalars. Okay. All right, so for vectors, something like a velocity is a vector because velocity has a sense of magnitude, which is the speed. Okay? But there's also a sense of direction. What direction are you traveling in? So for instance, saying like 10 meters per second north is going to be different from 10 meters per second east. So the direction matters. So velocity is a vector quantity. Other examples of vectors, velocity acceleration is also a vector quantity. Position and displacement, those are also vector quantities. And then just examples of something that's a scalar, so maybe something like a temperature. Okay. So temperature only has a sense of magnitude with it, like 50 degrees, 100 degrees. So obviously 100 degrees is more than 50 degrees. But you're not going to say that the temperature is pointing in any specific direction, right? You would just say like the temperature, in this room is maybe 72 degrees right now. But you won't say it's pointing in a certain direction. So temperature is an example of a scalar. Speed is the magnitude of the velocity. So speed is a scalar quantity because you're only talking about the magnitude and you're ignoring the direction of the velocity. Okay. Can you maybe think of any other examples of, say, a scalar or a vector? Like any that come to your mind?
A scalar could be like speed. All right. Well, you already said speed. Hold on.
Yeah.
A scalar could be like length, right?
Length, that's right. Length would be a scalar.
And a vector could be like a jerk or some other measure
Yeah,
of
jerk.
motion
Yeah,
like that,
okay.
right?
Yeah. So velocity is kind of like the derivative of position. Acceleration is the derivative of velocity, and then jerk is the derivative of acceleration, right?
Yeah.
So for those of you who maybe aren't too familiar with jerk, it's the rate of change of your acceleration is what it is. So, all right. So with vectors, so this class we're going to be dealing with vectors a lot, okay? So I'll talk about vectors quite a bit during this review and probably the next one as well. So vectors, we can visualize them as arrows. Okay. So if I draw an arrow like this, the length of the arrow is supposed to represent the magnitude of the vector. Okay. And then, of course, the direction that the arrow points in captures the direction of the vector itself, okay? So just sort of like as an example, if I draw a vector like this, and let's say that's 5 meters per second, and then I want to draw, so that's like a velocity vector there with magnitude of 5 meters per second. So if I want to draw a vector with magnitude of 10 meters per second, if I want to draw the picture to scale, then this vector should have a length twice that of this vector to represent the fact that its magnitude is double the original, okay? So that's what I mean by the length of the arrow corresponds to the magnitude. Now, two vectors are considered the same if they point in the same direction and have the same magnitude. Okay. So then these two vectors, they have the same direction, but their magnitudes are different, so they're different vectors. Likewise, these two vectors, they have the same magnitude, but they're different directions. So these two vectors that I've drawn are different from each other. But then if I draw another vector like this one here, okay, so then these two vectors, u and v, point in the same direction. And I try to draw it so that they have the same magnitude, so you can see that u and v are the same vectors, okay? All right, and then give me 1 second. So someone just joined in person now. So give me 1 second. All right, so I'm going to go ahead and zoom in because it's a little bit hard to see in person. Is that good? All right. Okay, so then I'm going to go ahead and start talking about like doing some arithmetic with vectors. Well, actually, before that, maybe I'll talk about one more thing, which is here we're representing vectors as arrows, but we can also represent vectors using coordinates as well. Okay. So then if, say here I've drawn a picture of the usual xy plane. Okay. So each point in the xy plane has a corresponding vector. Okay. So it starts from the origin and goes out to that point. So then the coordinates of that point could be used as a sort of algebraic representation of the vector. And in this class, you guys maybe haven't started it yet, but later in the semester for vectors, you're also going to be writing them as columns. So I'll go ahead and use column notation occasionally, just to kind of get you guys used to that when you start doing it more later in the semester, okay? All right. So here a vector with two components would be a vector that you're thinking of as being in the xy plane. And just some notation, that you guys are going to use in this class. So you guys might have seen this notation already, but if not, it's like R2. So this is just like a notation for the xy plane, basically. You can also say it's the set of all vectors with 2 components then, being in R2. Let's say 2 coordinates. Okay. And I won't do too many pictures in 3 dimensions, but certainly you guys will be doing things in R3 as well. So then just kind of as an analogy, R3 would correspond to like 3-dimensional space. So it'll have like X, Y, Z axes. Let's see here. Okay. All right. And then any vector, any point in R3 will give you a vector which starts out from the origin, and it'll have 3 components associated with it: X, Y, Z coordinate. And then you guys don't really go beyond 3 dimensions much in this class, but maybe occasionally a question might reference, say, like Rn for like some arbitrary whole number n. So this would just represent the set of vectors with n coordinates or n components. So you might represent those vectors as sort of a list of n coordinates like this. Or again, especially later in the class, you'll be often denoting vectors as columns. So it might look something like that as well. Okay. All right. So then with that out of the way, I want to finally start talking about some vector arithmetic. I want to start by talking about vector addition and how vector addition works. Okay. Maybe just I'll pause real quick and just ask if there are any questions about anything so far. Okay, all right. So again, if you have a question at any time, just ask away. For those who are virtual or remote, you can post a question in the chat. All right. Yeah, so let's talk about vector addition. So first, if you have vectors with coordinates, so here I'll assume that the vectors have the same number of components. I'll just use 3 components for an illustration. But to add vectors, you'll just add them component-wise. So it's pretty simple. So add the x's together, add the y's together, and then add the z's together. Okay? So vectors will have to have the same number of components in order to add them. So if they have like a different number of components, it wouldn't make sense to try to add them. Yes? So I guess that's a good question. Whoops. So let's say a quick example with some numbers. Okay, yeah, so for instance here, you should be able to add u and w. So you would do like a 1 plus -2, it's -1, 2 plus 5 will give you 7. Okay. Now, regarding whether you can add u and v, so I think I would say no for that because they have a different number of components. I know that sometimes, so thinking of this as a vector in the xy plane, sometimes you might add like a 0 z component to it, but I don't think that's something that you guys tend to do in this class. But I know occasionally you guys do things like that in your calculus courses, for instance. But in this class, I would say if it doesn't have a like explicitly written out like this, like a 0 for the z component, then I would assume it only has 2 components, and that's in R2. And so therefore you would not be able to add it to V, okay? All right, does that answer your question? All right. Yeah, so in this class, I wouldn't do things like that unless it maybe somewhere says that you can do that, okay? All right. So let's take a look at the example that we just did with adding U and W. So I'm going to draw just a little picture. So let's say here's vector U with components 1, 2. And then I'll draw a picture of vector W as well. So when we added the two vectors together, the result was this vector negative 1, 7, which should be about here. Okay. All right, so one observation to make about vector addition is here, if I form a parallelogram with like edges parallel to U and W, it's worth noting that the sum happens to be the diagonal of that parallelogram. So that's kind of a fact in general about adding vectors, like visually. So not just in this example, but in general. For two vectors, u and v, their sum, u plus v, is going to be the diagonal of the parallelogram. Formed by u and v. Okay. So that's u, and if that's v, so without like a coordinate system, you can still at least kind of draw a picture of what their sum would look like by completing the parallelogram, and then the sum is that diagonal, okay? Now there's kind of one situation where this rule actually doesn't work though. Can anyone think of a situation where this rule, where the sum is the diagonal of the parallelogram, where that wouldn't make sense? Close, yes, okay. So that's one case where it doesn't quite make sense. This is when the two vectors don't form a parallelogram at all, okay? So let's say like here's vector u, yeah, and then maybe like here's vector v, right? Well, in that case, they don't even form a parallelogram, so how could you draw the diagonal, okay? So there's another way to visualize vector addition aside from thinking of parallelograms. The other way to think of vector addition is if you connect the two vectors head to tail. So here I'll just kind of draw a picture. So let's say here's a vector u. And then I'm going to draw a vector v, but instead of connecting it here, I'm going to connect it to the head of u like that. Okay. So if you connect your vectors head to tail like that, then their sum is going to form the third edge of that triangle. Okay. This is sort of like a head to tail perspective for adding two vectors. You can see that it's the same as the parallelogram rule in this picture at least, because if I were to complete the parallelogram, that third edge at this triangle happens to be the diagonal of that parallelogram. Okay. So in that sense, these two produce the same result. Okay. So again, the sum is either the diagonal of the parallelogram, or if you connect the vectors head to tail, it's the third edge of the triangle that they form. Okay. This alternative perspective works better in these types of situations as well, though. So here you don't have a parallelogram, but you can still, in theory, add them using the head-to-tail method. So here what I'd have to do, though, is I'd have to redraw my picture. So that's u. I would need to connect v to the arrowhead of u. So maybe like that was v, right? Okay. And then their sum would actually be, let's use a different color. So let's say that's v. Right, then there's some intended, but that's okay. Would be this vector here. Oh geez, u plus v. So I guess I selected the highlighter, I think, rather than the pen. Or just a really thick I see. Okay. So to see how that works, for the head to tail method, the sum, I guess it starts from the beginning of the first vector and it ends at the end of the second vector. So here I drew it so that it started at the beginning of u, but it ended at the head of v. So then that would represent u plus v. Okay. All right, so then that's just kind of the gist of how vector addition works. So in terms of the coordinates, you just add them component-wise, as long as they have the same number of components. And then you have a couple of different ways of visualizing vector addition, the parallelogram rule and the head-to-tail rule. I want to, before I move on to something other than vector addition, I just want to kind of do like two more small examples. So I talked about how like some examples of vectors were like position, velocity, acceleration, and things like that. So just thinking of an example in terms of position. So then let's say that here's our origin. And then we have the vector, let's call this vector u. Oops. And maybe this vector represents our current position relative to this point, okay? So like right now, that's our current position. And then let's say we're going to change our position now. So from this point where we're currently at, we're going to travel to this new location. And let's say that this vector was v, and then this is our new position. Okay. So the new position could be represented by the vector u plus v then. Okay. So here you can maybe see how, or maybe it makes sense to think of how the head to tail method works when you think of position. So it's just saying, you starting from this initial point, you move to here, and then you move to here, and then we're just saying that's just equivalent as starting from here and moving to here. Okay. So if you think in terms of position, I think maybe the head to tail method of addition maybe makes a bit more sense. And then just like another quick example. You guys have probably seen questions like this before, maybe in like a physics class, where maybe you're in some kind of vehicle, like an airplane, or maybe let's say that you're on a boat or something. So let's say you're rowing your boat and you're pushing straight forward like this. And let's say the velocity that you are rowing at is maybe like, 5 meters per second or something like that. But then in addition, you've got the water, which is actually flowing in this direction. So I use W to represent the velocity of the water. And let's say the velocity of the water was, maybe 2 meters per second or something. So then what's the overall velocity that you are traveling at? So that overall velocity would be represented by the vector sum. So it's the sum of your rowing velocity with the velocity of the water. Okay. So I guess what I want to point out is, like, when I talk about vector addition, it might have seemed kind of like abstract, like why is it that we add vectors like that? So I guess what I wanted to highlight with these two examples is this is how vectors actually add, like in, quote unquote real life. They actually add this way by the parallelogram rule, or if you will, by the head to tail rule, which both produce the same result. Okay. All right. I think that's enough about vector addition for now. So let's move on to a couple more topics. I want to briefly look at vector subtraction. Okay. So maybe does anyone know how vector subtraction works, like visually? Any idea? It's similar, yeah. Yeah. So it's similar to addition. So maybe first, just in terms of coordinates first, it's basically the same, just do it component-wise. Okay. So I'll use vectors with two components just to illustrate. Yeah, so subtracting them again, it's just going to be subtract the x components, subtract the y components, and so forth if there were more components, okay? Right, but then in terms of a visual, let's say if I'll draw the vector u and I draw the vector v. Okay. Where would the vector u minus v fit in this picture? Yeah, okay, so yes, yeah. So let's think about it. So u minus v is the same as u plus minus v. So minus v just changes the direction. So what I'm going to do is just kind of negate v. And I'll talk more about that when I get to scalar multiplication as well. But yeah, so minus v just points in the opposite direction. So then if I were to form a parallelogram here, then u plus minus v would be that vector there that I just drew. Shift u up to here. Now, in terms of kind of the original vectors over here, notice that this vector u minus v would be the same as this vector that I'm going to draw up here. Okay, so that's also u minus v, just starting at a different location. So I guess what I wanted to note is that u minus v completes this triangle formed by u and v. Okay. So if I kind of erase or just focus on the top part of the picture, and that's u and that's v, this would be u minus v. Okay. So that's very similar to vector addition, right? Vectors u and v form two edges of a triangle. And then we talked about how the sum and the difference complete the third edge of that triangle. Now the difference between the two though is with vector addition, remember that u and v are connected head to tail. Okay. And then when you connect them head to tail, their sum is the third edge of this triangle here, okay? With vector subtraction, instead of connecting u and v head to tail, notice that I have vectors u and v connected tail to tail in the picture, right? So when they're connected tail to tail, the third edge of the triangle is their difference, not their sum, okay? Also maybe worth noting the direction that the difference points in. So when we do u minus v, it points like in the direction from v to u, right? So the way that I kind of remember the direction is, I kind of think of it as like the final minus the initial. It's kind of how I remember it, in the sense that the difference u minus v, it ends at u, so that's like the final location, and it started at v, so v is like the initial, okay? So final minus initial helps you determine the direction that the difference would be pointing in, okay? All right. Let's talk about scalar multiplication next. All right, so we talked about earlier a scalar is a quantity that has just a sense of magnitude, no direction. Mathematically, you can think of a scalar as just being a number, okay? So here we're talking about how to multiply a vector by a number. So let's say v has components x and y, and c is just a number. If we multiply the scalar c with the vector v, so in terms of components, all you do is multiply the scalar to each component, okay? So I'll draw just a little picture so that we can visualize what's going on. So let's say vector v, I'll give it components 2, 1. Okay. So if I multiply vector v by the scalar 2, that's going to produce the vector 4, 2. Okay. And so if I were to draw the vector 4, 2 in my picture, it would look like that. And what you guys will notice in the picture is that 2v is just double the vector v, like double the length, okay? So that's kind of good to know, is that when you multiply a vector by a scalar, it will scale the magnitude by that same amount, or by that same factor. So let's see here, if I were to write that in words, you could say maybe CV well, let's write it like this. So what we're saying is multiplying a vector v by a scalar c will multiply the magnitude by c as well, okay? Okay, now, this is assuming that c is positive though. So maybe what happens when c is negative? So we kind of already talked about that. But when you multiply a vector by negative, what that does visually is it reverses the direction. So you can see in the picture how that works. Minus v points in the opposite direction of v, okay? So when you multiply by a negative number, it reverses the direction, in addition to scaling it by the magnitude of that scalar, okay? Okay. So with that out of the way, that mostly covers what I wanted to cover regarding vector addition, subtraction, and scalar multiplication. So I want to talk about linear combinations next. So maybe before I start talking about it, can anyone just tell me what a linear combination is? Okay, all right. So yeah, let's talk about what a linear combination is. To do that, I'm gonna draw a picture as well. See here, let's maybe start the picture here. So here's a vector u, and maybe I'll draw a vector v like this. Okay. I'm gonna create the parallelogram that they form. And so we talked about how the diagonal of this parallelogram, so we know this is vector u plus v, okay? So u plus v corresponds to the very tip, so at the very corner of the parallelogram like that. So if I want to think about another point inside this parallelogram, so I'm going to pick a random point. Let's just pick this one here. How would this vector relate to u and v? Any ideas? Yes. This red vector. So it's I've drawn it so that it's inside this parallelogram formed by U and V. Can we maybe describe it somehow in terms of U and V? Okay. So we can do that. Yes. Yeah. Okay. So what I'm gonna do, yeah. No, that's the right idea. So I'm going to draw like a mini parallelogram. Okay. So then here I've got these two vectors and this. Let me give this vector. Oh no, it's fine. So this vector here is the diagonal of this mini parallelogram, right? So you can say that this vector is the sum of these two vectors. Okay. Now these two vectors, they point in the same direction as U and V, but they have a different magnitude. Okay. Now because they point in the same direction, you can think of them as a scaled version of U and V. So this vector here is U times some scalar, we'll call it C. And then likewise, this vector here is going to be some scaled version of V, and I'll call that scalar D. Okay. And then this vector that we were looking at originally, you can now say is a CU plus DV. Okay. It's going to be that vector there. And we can say a little bit more information about the coefficients, the scalars C and D. So both of them should be positive, right? Because vectors C, U, and dV are pointing in the same direction as U and V. So if they were negative, they'd be pointing in opposite direction, right? So these have to be larger than 0. What else can you say about C and D? So they're larger than 0. Can you say that they're smaller than a certain number? Mm-hmm. Where? Oh, it's a small arrow. Yeah, yeah. Mm-hmm. Yeah. Mm-hmm. Right. Okay. Okay, so yeah, so what I wanted to say was, so I was trying to just, because I felt like this was too far away from the vector, so I wanted to somehow connect them a bit more. So I wanted to draw an arrow, but then I thought it might be confused as a vector, so I tried to squiggle it is what I did, but yeah, that's fine. But yeah, so what I want to say though is C and D. So in this picture, they have to be positive because CU and DV point in the same direction as U and V. But they're also shorter than U and V, right? So both CU and DV are respectively shorter than U and V themselves. So that means that C and D, these scalars, they have to be smaller than 1. Okay. Because if they are larger than 1, then these vectors would be larger than U and V, but they're not. Okay. So to get a vector that's like inside of the parallelogram, right? It's going to be like a scalar multiple of U plus a scalar multiple of V. And those coefficients are going to be between 0 and 1. Okay. But right now, I don't want to focus too much on this restriction. I just want to focus on this expression that we have here. So it's like a sum of scalar multiples of our vectors. And that's what we mean by a linear combination. Okay. So whenever you hear someone talk about a linear combination of vectors, they're referring to like a sum of scalar multiples of those vectors, okay? So if I were to write that out like a bit more precisely, you could say that a linear combination of, let's say you have some vectors v1, v2, etc. Okay. So linear combination of vectors v1 through vn is any vector of the form c1 v1 plus c2 v2 and so forth plus cn vn. Okay. So again, linear combination is just a sum of scalar multiples of your vectors. So then just as like a small example, let's say I'll create two vectors on the spot here. So vector 1, 2. Let's say this is negative 2, 3. So if I scale my two vectors, let's compute maybe 2 times v1. And let's maybe do like plus just 1 times v2. So 2v1 would be 2, 4 plus 1 of v2 produces this vector 0, 7, right? Okay, so we could say that vector 0, 7 is a linear combination of vectors v1 and v2, okay? And we can see that because we know that 0, 7 is a sum of scalar multiples of v1 and v2, okay? So I'll do a couple more examples, but then I'm going to also return to my picture in a bit. But let's do a couple more examples first. Okay, so here I kind of cheated though, because I started with the linear combination to compute this vector 0, 7, right? So instead, what if we start with a vector first and we ask is it a linear combination or not? So let's see here. Let me make up two numbers. Let's do 3 and 2. So let's say we want to know is vector 3, 2 a linear combination of v1 and v2. Okay. Okay, so how are we going to figure that out? So let's say we want to check, can we express 3, 2 as a sum of some scalar multiples of v1 and v2? So that gives us sort of an equation to set up. Okay. So what we'd like to do is try to solve for C1 and C2 to see if this is possible or not. So to solve for C1 and C2, if we multiply out the right-hand side, so multiply and add everything up. So you'll get like 1 C1 minus 2 C2. And then here you'll get like 2 C1 plus 3 C2. So for these two to be equal to each other, so for two vectors to equal, their components have to coincide. Okay. So from that, you get kind of two equations. So C1 minus 2C2 must be equal to 3. And that 2C1 plus 3C2 must be equal to 2. And then here, let's try to see if we can solve for C1 and C2. So you can solve this equation by doing substitution or elimination, right? I think what I'll do is I'll do elimination. So I'm going to multiply this first equation by 2 on both sides. So I can get like a 2C1 on the right-hand side. And then here, if I subtract the two equations now, I'll be able to cancel out the C1s. We'll get 6 minus 2 is 4. Negative 4 minus 3 is minus 7. Okay. So therefore, we solve for C2 as being negative 4 over 7. Okay. And then let's just go back and solve for C1 real quick. So I'm going to take the first equation, and I'm going to plug in the result for C2. Okay. And then from there, we'll be able to solve for C1. Okay. So if you move the 8 over 7 over to the other side, 21 minus 8, so 13 over 7, if I did my math correctly. Okay, so then we managed to solve for C1 and C2. So then going back to the original equation that we had up here, okay? So that means that vector 3, 2 should be equal to C1 being 13 over 7 times V1 plus, well, C2 is negative, so let's do minus 4 over 7, and then V2. Okay. So we see that vector 3, 2 is a sum of scalar multiples of V1 and V2. So therefore, we could say it is a linear combination of V1 and V2, okay? So therefore, 3, 2 is a linear combination of vectors V1 and V2, okay? All right, so I'll pause for a moment and just ask if there are any questions. Okay, all right. So lastly, I want to talk a little bit more about visually, how can we think of linear combinations, okay? So here we saw that if we take a linear combination where the scalars are between 0 and 1, that produces a vector that's inside of the parallelogram formed by u and v. Okay. So you can say that the parallelogram, whoops, okay. All right, so this parallelogram formed by vectors u and v can be thought of as the set of all linear combinations where the coefficients are between 0 and 1. If I want to include like the edges of the parallelogram, I could allow C and D to be equal to 0 or 1 as well. Okay. So then that just means that any vector that you try to draw that's going to be somewhere inside the parallelogram, it's going to be a combination of U and V where these coefficients are between 0 and 1. So if we change the range on C and D though, that's going to affect the picture a little bit. So let's consider like I'm going to redraw my picture down below, and I want to consider like different linear combinations. I want to think about what those linear combinations look like. So let's come down here, and I'm going to draw another picture. Let's maybe I'll draw my picture like this. Okay. Okay, so then again, just a quick repetition. So we can say this parallelogram consists of the linear combinations where C and D are between 0 and 1. So if we change the range on C and D, so let's say I make C between 1 and 2, but I keep D between maybe 0 and 1 for now, for this first one. So do we know like what kind of picture would be associated with like this range of linear combinations? Yes, yeah, so any vector that I draw inside this parallelogram here, so whether I draw like this vector or like that vector or like this vector, right? Okay. So as long as the vector is inside of this parallelogram, it's going to be a linear combination of U and V. Okay. And yeah, what was that? Yeah, it can be expressed as a linear combination of U and V, and specifically the scalars, the coefficients are going to be between 0 and 1. Okay. So it's the same idea as what we saw in the earlier picture where you can form like a mini parallelogram and make the argument that some CU plus some dV, but the C and D are going to be between 0 and 1 to make that work. Okay. So with the coefficient between 0 and 1, it's going to give us this parallelogram. Okay. So if we change range on the coefficients though, it's going to take us outside of the parallelogram now. So my question is like, if maybe I change the range on C to be between 1 and 2, where are these linear combinations going to be in the picture? Okay. Okay. So we can maybe think of a couple of examples just to try to get a sense for where would these linear combinations reside within the picture? So we're restricting C between 1 and 2, so maybe let's look at the sort of extreme cases. So like what happens when C is equal to 1? What happens when C is equal to 2, right? Let's set D to be 1 as well. Let's look at these two vectors first. Okay. So let's maybe graph these two vectors and see where they're going to be in the picture. Now let's see, we know that U plus V was the edge of this parallelogram here. So that's U plus V. Okay. Now 2U plus V, so if I like change C to be 2, okay. What we'd have to do to draw that vector is I'd have to double the length of U first. So maybe imagine like that's a second copy of U. So then if this is a 2V, then 2U plus V will kind of be up here now. So that's 2U plus V. That's, I guess, 1U plus V. I'll emphasize the coefficients maybe as well right now. Okay. All right. Okay. So if I restrict C to be between 1 and 2, we kind of see that it kind of places us in between these two vectors. Okay. So it's kind of between like 1U and 2U altogether. Now D is restricted to be between 0 and 1. So here I did some combinations with D being equal to 1. Okay. Maybe if we just consider the case where D is equal to 0 as well. So just kind of considering the different extremes right now. Okay. So if I set D to be 0, but keep C between 1 and 2. So I'll set C equal to 1 and 2 to think about what are the extreme cases. So of course, this is just a U and 2U. Okay. Oops, that should be U. Okay. Okay, so then let me emphasize those two vectors. So here's U. And okay, and then here's 2U. Okay. So when we look at these 4 vectors here, they end up forming the corners of another parallelogram. So let me draw that parallelogram in this picture. Okay. And then if we try to think about, here I specifically chose C and D to be like the edge cases. But if you think about maybe like a number in between 1 and 2 and a number in between 0 and 1. So let's just maybe pick something that's in the middle. So say if like C is like 1.5. And if D is maybe like 0.5, so something between 0 and 1. So we want to think, where would this vector be in the picture? Okay. So let's see, if I try to draw this vector here, so it's 1.5W, so it's like 1.5, right? So it'd be about here. It's 1.5 of U. Okay. And then like 0.5V, so it's like half of V, so it'd be like right there. So if I add the two of them, it produces this vector that's over here, okay? Okay, so it places us inside of this parallelogram as well, okay? So if you kind of continue playing around, picking different combinations where C is between 1 and 2, D is between 0 and 1, and you keep trying to draw those vectors and see where they are, what you'll end up finding is that those linear combinations are inside of this parallelogram here, okay? So I'm going to redraw the picture real quick because it's a little bit cluttered. So here's the original V and U. And so we said that originally we saw that the linear combinations where C and D are between 0 and 1 place us inside of this parallelogram. If we adjust the coefficients a bit though, so if we have C being between 1 and 2, those linear combinations are going to fall into this parallelogram instead, okay? So there's kind of the way that I kind of think about it is you can kind of think of these coefficients as like coordinates and U and V as like your coordinate axes. Whoops. So here, let me emphasize the coefficients in front of the U and the V. Okay. All right. So here, when we have the C ranging from 1 to 2, so it kind of places us to be like in between 1U and in between 2U. Okay. And then D being between 0 and 1, so it's between like 0V and 1V. Okay. So since it has to be between 1U and 2U, and then it also has to be between 0V and 1V, it kind of puts you inside the second parallelogram. And that's kind of what we were seeing earlier when we were kind of doing some examples to try to visualize it, okay? If I choose like other linear combinations, so let's maybe think, let's do one more. Let me choose a different color first. Let's do orange. It's kind of thick. Let's do a thinner version, okay. So if I change the range on the coefficients once again, this time let's do something maybe a little bit more complicated. So let's say I have C ranging between -2 and 0. And then let's say I'm going to have D ranging between maybe 3 and 6. So I want to think about if we were to draw these linear combinations in the picture, where would they fall? Okay. So here, yes, yes, yeah. So I'm planning on wrapping things up after this. Yeah. You can leave though if you need to go. So there's nothing. Okay. Yeah. All right. You can always leave at any time. I can't. I mean, I'm not going to try to. Yeah. No, it's unlocked, so it should be fine. Yeah. So let's see here. So if we want to think about it, so C is affecting vector U, and we're ranging it from 0 to -2. So in the picture, let me kind of go out to -2u first. So this is a 0 u's, right? Let's say that's about -1u. And then let's say this is about -2u, would be about there, okay? So since the c has to be between 0 and -2, that tells us that these linear combinations are kind of falling within this band right now between 0u's and -2u's. So that's what we get from like c being between -2 and 0. Okay. Now let's look at d. So d is between 3 and 6. Let's make the number a little bit smaller just to make the picture nicer. So let's put it between 3 and 5. So we need to, since d is affecting v, so let's look at where would 3v be in the picture, and let's look at where 5v would be in the picture as well. So this is 1v here. So this is about 2v's. If I go up a little bit more, this is kind of 3v, okay? 4v would be around here or so. And let's move this up a bit. If I go up to 5v, it's maybe about here would be where 5v would stretch out to, okay? Okay. All right, so let's see here. We need to be between the 3v and the 5v. So that's the linear combinations that we're trying to visualize right now. Okay. So let's see here. This is 3 and 5, so it has to be between these two. So I'm going to draw a little band in between them. Okay. All right. Okay, so D being between 3 and 5 places us between these two. And C being between -2 and 0 places us between these two. So altogether, it seems to describe this kind of parallelogram region. So vectors which stretch out to this area would be a linear combination where the C was between -2 and 0, and the D was between 3 and 5, okay? So different linear combinations are going to fall into like different regions in our picture, okay? So like when C is negative, it falls to the left of where we started. If D were negative as well, it would fall underneath the picture. So like when you're scaling V by a negative number, that reverses the direction. So D being less than 0 will put you like underneath everything, okay? But here I just wanted to do a couple of things. So just kind of visualizing linear combinations as corresponding to like different regions in the picture. And then I also just want to end with like a sort of a question, which I'll also answer. But if we didn't put any restriction on C and D at all, if we just consider all possible linear combinations of U and V, what kind of picture would that end up describing? So if we consider all possible linear combinations. So if we allow C to be like any number from minus infinity to positive infinity, and if we also allow D to be between minus infinity and positive infinity, what kind of region is that going to end up describing in our picture? So I don't know if you have any ideas on that, or anyone. Okay, yeah, so if there's no restriction on C and D whatsoever, you'd be able to fill out the entire plane, if you will, formed by U and V. So then, yeah, set of all linear combinations of U and V would correspond to the plane formed by the two vectors. So let's say that you can visualize a set of all linear combinations as the plane formed by U and V. And when I say plane, I kind of mean like the entire infinite plane that they form. So like if you were to try to shade in the picture, it would just be like shading in everything. Okay. So the whole plane that they lie in would correspond to the set of all possible linear combinations of them. Okay. Okay. So the set of all linear combinations of some vectors that has a name. So that's referred to as the span of the vectors U and V. Okay. So here we kind of see that the span of two vectors ends up forming a plane, at least in the picture that we have here, okay? So with the vectors U and V in our picture, their span is the plane that they create. And it's like an infinite plane stretching out in all directions, okay? I guess I'm gonna go ahead and end my review here today. And then we'll talk a lot more about vectors next time as well, so.